The bottom line is we can create structures that have not been able to be created before and are applying them in ways that have not yet been applied, specifically to flowing lots of air through these materials or flowing water or flowing some sort of reaction through it. We're building a machine right now that can produce these structures that are really high surface area and really porous faster than has ever been able to be done before, and cheaper as well. These kinds of structures are really useful for all sorts of applications, especially in including direct air capture of CO2. What we can do with these structures is maximize surface interaction rates of reactants to make products. So that can be CO2 to adsorb onto their surface, or interestingly, we can also apply this to filtration in general or reactions in general. So this has large application space. However big you think supernova are, they're bigger than that. And I think that's what climate tech is going to be like.
What brought you to work in climate tech?
You know, I have always been inspired by life in general.
You're listening to Bite Size Climate Tech, Season 3.
We're on. Hi, John.
Hi, Lydia.
I'm so happy to have you today. John Slack is the founder and CEO of ROIC, a company focused on revolutionizing direct air capture technology to reduce the costs of carbon capture using advanced material science. Welcome to the show, John.
Thanks for having me. I really appreciate you bringing me on.
If you want to add a few sentences about yourself, if I missed anything.
Sure. Yeah, I started my career in climate in the green hydrogen space. So I've been working in material science, polymer science, electrochemistry for fuel cells and electrolyzers to make and use hydrogen from water.
So talking to scientists and engineers is always my highlight of the day. And today I'm really excited because I'm going to learn about the technology behind your company, ROIC, the fast nanofiber manufacturing.
What we do is we make nanofiber materials really fast and really cheap. We're building a machine right now that can produce these structures that are really high surface area and really porous faster than has ever been able to be done before, and cheaper as well. So these kinds of structures are really useful for all sorts of applications, especially in including direct air capture of CO2. What we can do with these structures is maximize surface interaction rates of reactants to make products. So that can be CO2 to adsorb onto their surface, or interestingly, we can also apply this to filtration in general or reactions in general. So this has large application space in terms of all of climate. So really, it's a new manufacturing technique that can hopefully enable lots of other industries in climate tech. That's as a preamble, and then to get into how it's done, we take a polymer solution, as long as that polymer is high enough molecular weight, meaning it's really long chain. Think of like spaghetti, lots and lots of very long spaghetti, and we have that in solution, and we can even mix in nanoparticles into that. So maybe think spaghetti and meatballs, but small, very, very small. And we then apply an electric field to that solution. From that electric field, we can draw out many, many nanofibers. So this is a form of electrospinning technically, but it's new in terms of the electronics that we're using and the waveform that we're using for the field. The bottom line is we can create structures that have not been able to be created before and are applying them in ways that have not yet been applied, specifically to flowing lots of air through these materials or flowing water or flowing some sort of reaction through it. And the name ROIC comes from the Greek word roi, which means flow. So the idea is we can flow lots of material through this to help reverse pollution.
Let me try to step back a little bit. Because I interview people who has done, for example, fluidization or their enhanced rock weathering in a different way, right? 'Cause the basic, like what you said, is increase the surface area. My understanding, your technology is more towards the direct air capture, make the whole process more efficient and lower cost. You have this structure, which you explain, like pasta, like the polymer structure. When you're doing this on the nanoscale, it's even faster than what the other people they're doing for the rock is rock dust. And then the next phase is people are doing powder. And then you're in the next level of the scale and have some way to supercharge this process so it's like faster. in a way.
Correct. Yeah. So maybe I can break this down into its components as well
Yeah,
for you.
because
So
I know direct air capture, you have 3 steps. You first need to gather the air, and then you flow it through some sorbent or solvent, and then you capture it. So yours technology is which step?
yeah, so all of what I've said so far is making the stuff that will be put in that process.
Okay.
So I'm making the catching material. Like this is the stuff that will do the carbon capture. So
Okay.
the goal would be to provide these materials to other direct air capture companies.
Mhm.
Or interestingly, because the materials can be versatile, we can provide these to point source capture companies too. So this is something that can apply to both direct air capture of carbon dioxide, but also slipstreams of flue gas in natural gas or coal. Any small or big emitter can utilize these structures because they're able to be more durable and withstand pressures and temperatures in these applications too. So like I said, it's a versatile set.
The reason why it can apply to the point source, and you said it's versatile, is because it's not only applicable to ambient air, but also can work when people in the point source, it's like very pollutant, the flow of the whatever that is. Right.
Right. The reason we can do this is because we can tune the materials. There's a large variety of polymers that we can use, and
Yeah.
we can make them very durable structures with very low pressure drop, meaning it's easy for the flow to happen.
So you're manufacturing this material, which makes it very versatile for not only direct air capture, but also other point source capture application as well.
How would you explain this to an 8-year-old?
What I would say is picture cotton candy. You have a cylinder of what looks like kind of fibery material, but instead of made of sugar, it's made of special other material. And we can flow a lot of air through this cylinder of cotton candy. And as we flow the air through it, there's CO2 coming in and clean air coming out.
Nice. It's a good way to put it. The next segment is you're going to answer a question from a previous guest. So her question is whether it's the public sector or the private sector that's going to drive climate tech adaptation and implementation.
The way I will describe at least my perspective on this is that the public sector can get things kickstarted, and that's been shown in lots of different arenas, including solar. China have had huge impacts in terms of driving costs down, but then at some point it is required that the broader market have a demand signal that can sustain that progress. I see it as if the question is what's going to drive adoption, the answer is both, because you need to get it kickstarted to bring the cost curve down and to drive technologies up the technology readiness level scales. That's very risky for markets in general, which is where the public sector comes in. But ultimately, I think that the private sector has to continue for it to be sustainable. So that's my answer.
I think the difference between now and maybe like 10 years ago is, well, continuously, if we don't do anything and if we just wait for one part of the world to take action, then it's going to be too late for everyone. This movie, everything, everywhere, all at once. I think that's what we need.
There's a phrase that I have heard in astronomy that is, however big you think supernova are, they're bigger than that. And I think that's what climate tech is going to be like, is in terms of both the economy and size of the problem, but size of the opportunity. We're at a really interesting juncture in human history where everyone is facing the biggest problem we have ever faced. And that gives us an opportunity now to come together to solve it. And if we do that, what we have done is come together. That's, I think, the most exciting part of this, that because it's affecting everyone, we now have a common enemy for us to rally together and have some sort of uniting force. So that's what gives me a lot of excitement.
Yeah, exactly. That's why the reason why we're having this kind of conversation. If you can leave a question for the next guest.
Yeah. The question is, what makes you feel most optimistic about the future of the state of our climate?
My next question is, what brought you to work in climate tech?
I have always been inspired by life in general. If you look around, if what we want is for humanity to continue existing, which that's what it means to be sustainable, to continue sustaining, what better source to look at than the billions of years of R&D that are around us? So biomimicry at the grandest scale, I think, is what we have to employ. I feel very inspired by trying to mimic life in that way, and that's what brought me into climate.
For the future millions of years to come.
Yeah, exactly.
Let's make
Let's make climate cool again.
cool again. Yes. Thank you so much, John.